There's an interesting way to think about what it is exactly that second order homogeneous linear differential equations are doing in terms of linear differential operators. So here's the sort of second order constant coefficient homogeneous linear differential equation that we've been solving. And, sure enough, we can solve this using the techniques we already have. We can translate this into a characteristic equation, which would give us m squared plus 5m minus 14 equals 0. And this factors, this is m plus 7 times m minus 2 equals 0. And so this gives us m is minus 7 or positive 2. And that means we have two linearly independent solutions. The first one is e to the minus 7x. And the second one is e to the 2x. Okay, so that's fine. But there's another interesting way to look at this, which is, we have this linear differential operator notation where capital D sort of stands for the operator d dx. And if we use that notation to rewrite this differential equation, we get capital D squared y plus 5 capital D y minus 14y equals 0. And remember how we rewrote this was we sort of saw that y is being acted on in each term, and so we sort of quote unquote factored out the y. It's not really factoring since this operation here isn't multiplication, it's application of a differential operator, but it sort of looks like factoring. And the remaining linear differential operator is d squared plus 5d minus 14. Okay, so our original differential equation now looks like, if we call this stuff in parentheses, call this linear differential operator L, then our original equation is now just that linear differential operator L equals 0. Okay, well, what does this have to do with solving this sort of equation? It seems like it's just a notation trick at this point. Well, the idea here is L is sort of a polynomial where the variable isn't a variable, it's actually the differential operator d. So L is d squared plus 5d minus 14. And since it's a polynomial, we can factor it. This factors as, it factors just like the characteristic equation did. It's d plus 7 times d minus 2. Okay, so what we're really looking for is, to solve this differential equation, what we're really looking for is a solution to d plus 7 times d minus 2 applied to y equals 0. And there are a couple ways this can happen. So if you think, remember a differential operator, it does some combination of derivatives and adding the function to itself. So if you start with some function y and you apply d minus 2 to it, right, you get y prime minus 2y. And then after that, you would apply d plus 7 to that. And that would give you y double prime plus 5y prime plus minus 14y. Right. So again, it still sort of looks like, well, we're just rephrasing what the original differential equation was. But if you look at this version of writing the differential equation with the factored linear differential operator, we've actually made an easier equation for ourselves, because if this middle section here, d minus 2 applied to y, if that comes out to be 0, it doesn't matter what d plus 7 does, because it's hitting the function 0, and so you would just get 0. So factoring it lets us see that we can rewrite this equation as not rewrite, but rephrase this equation as we're looking for solutions to d minus 2 applied to y equals 0. And this is really a first order equation. This is just the first order equation y prime minus 2y equals 0. And we have enough experience with first order linear differential equations to know just kind of by looking that the solution to this is, or a fundamental set of solutions for this equation is e to the 2x, right? So first order equations, first order constant coefficient equations, we can solve basically just by looking at them like this. So that gives you one solution. And right, this is one of the solutions in the fundamental set that we figured out at the very beginning. But what about the other solution? Well, here's the magic of constant coefficient equations. Because these are constant coefficient differential operators, we can actually turn them around like this. They commute. Now that might look obvious, but I'll show you in a minute that this is actually a special property of constant coefficient differential operators. So since we can turn them around like this, rather than looking for solutions to this first order equation, we can now notice, well, we've got this other first order equation, d plus 7 applied to y equals 0, which is really the differential equation where y prime plus 7y equals 0. And this has a solution that, again, you can write down just by looking at it. It's e to the minus 7x. And that's the other solution in the fundamental set that we got at the very beginning. So the reason that second order equations, when their characteristic equations factor, the reason that second order equations are so easy to solve is because this property of these differential operators commuting lets you just think of the second order equation as two first order equations. So again, this is happening because these differential operators, these first order differential operators, commute. Let's check that that is actually true. So it is sort of a not very interesting exercise in multiplying things out. So the operator d minus 2 times the applied to the operator d plus 7, right? This would be the operator d minus 2, right? The d minus 2 is a linear differential operator, so it distributes like this. So that's d minus 2 applied to whatever d produces, plus d minus 2 applied to whatever 7 produces. But then we can, right, linear differential operators distribute, so we can actually distribute this the other way, like this, like this. I guess that's really the definition of the linear differential operator. So this gives us d applied to d minus 2 applied to d plus d applied to 7 minus 2 times 7 is 14. Now we do have to be a little careful about interpreting this. So d applied to d, remember that really this is taking place in a context where there's some function that we're acting on like this, some function y. And so d applied to d is really d applied to d applied to y, right? There's sort of an implicit function that we're acting on. And so if you started with y and you did d to it and then you did d again, what you actually did was d squared. You did it twice. In other words, a second derivative. Okay, minus 2 times d, right? Because if we were acting on y, 2 times a derivative would be 2 times the derivative of y. So we get 2d here, plus, now here for this term, this d7 term, we have to be careful because it's important to remember this, that we're imagining that we're acting on a function y, because d applied to the operator 7 applied to y, right? This isn't the derivative of 7. That's not what this notation means. 7 here is really shorthand for the differential operator 7 that doesn't take any derivatives. It just multiplies the function by 7. So this is really d applied to 7 applied to y, but 7 applied to y is 7 times y. So this genuinely is multiplication. And then the constant multiple rule for derivative lets us move this 7 outside. So 7 times d applied to y, like this. So this d7 term is actually the same as 7d, right? Because right here we have d7 and here we have 7d. So these are actually the same, right? And again, right here where we moved this 7 outside the derivative, this is where we are using the fact that this differential operator is a constant coefficient differential operator. Okay, minus 14, and then of course we can combine the like terms here, d squared plus 5d minus 14. Okay, and notice that's the linear differential operator that we got from our equation to begin with. So if we did this the other way, so remember the whole point of this is that these linear differential operators commute. You can do this in either order. If we did exactly the same calculation, we get, let's see, d, so this one is d applied to d, that's d squared. D applied to minus 2 is, we are careful here, this is minus d applied to the operator 2, and then plus 7d, and then minus 14. So d squared. Now here again, we can move this 2. These two operators, d and 2, commute because 2 is a constant multiplication operator. So minus 2d plus 7d minus 14. And you see we get the same thing, d squared plus 5d minus 14. So because these are constant coefficient linear differential operators here and here, it doesn't matter which order you do this multiplication in. You get the same second order linear differential operator either way. If your linear differential operator is not a constant coefficient operator, it actually can matter what order you do the multiplication in. So let's look at an example. Let's calculate what is the result of the operator d plus x applied to the operator d minus 1. Now again, as we calculate this, we need to remember that really, since operators act on a function, there's an implicit function that these derivatives are acting on. Okay, so distributing this, we get d times d, so that's d squared, and then d applied to minus 1, so that's minus d applied to 1, but we can move that 1 inside or outside this d, so we don't really need to write it down. Okay, now here is plus x applied to d, and then minus x. Okay, now remember these last two terms here, x applied to d minus x, remember there's an implicit function y that we're acting on here. So the operator x is really the operator that multiplies your function y by the function x, and the operator xd is the operator that first takes a derivative, and then after you've taken the derivative, multiplies by x. All right, so that's what you get when you multiply these two first order operators in this order. So now let's multiply them in the opposite order and see if you get the same thing. I mean, I hope I've foreshadowed that you don't get the same thing, but let's check why. Okay, so d applied to d, that's d squared. D applied to x. So here we have to be very careful. Remember, there's an implicit function y. So let's do d, the operator d applied to x, applied to y. Now by definition, remember this is not the derivative of x. That's not what this means. This x is an operator that represents multiplying y by x. So this is d applied to x times y. So we're taking a derivative of x times y, and that's the derivative of x times y plus x times the derivative of y. That's just the product rule. Now this dx genuinely is the derivative of x, and the derivative of x is 1. So this is y plus x dy. And if we were to write this as a linear differential operator, we would write 1 plus xd applied to y. So this dx term right here results in this operator, 1 plus xd. Okay, now we can finish distributing. Minus 1 times d, that's just minus d, and then minus 1 times the operator x is minus x. Now if you compare these two, they both have d squared, they both have a minus d, they both have an xd, they both have a minus x, but the second one has this extra plus 1. So these two ways of writing, these two orders of applying these linear differential operators do not give us the same thing. So what we'll see is second order differential equations that do not have constant coefficients, you can't reduce them to first order equations like we did with constant coefficient differential equations. And really it's because of this. It's because you can't decompose second order linear differential operators into first order linear differential operators in a way that commutes.